Okay. Okay, so this is OVSDB on conference session. We've been through a couple sessions already today, and they've been kind of, we're typically used to just sitting around the whiteboards and kind of working through the development issues. And it seems like this has been an information transfer kind of sessions, which we're finding kind of difficult to work with. So what we're going to try to do is we've got, we'll start this by just trying to describe the features that we're thinking we're going to implement for Beryllium, and then we're going to pick a couple and try to just start working through those, and then maybe we can work from that. So this is a slide we presented on Monday. You can see we've got clustering. We're not going to talk about that today because it's a pretty big problem. Code quality issues, we won't really talk about that piece. Security groups we won't talk about, but SFC and NFV integration, I think that's a big one for us we want to talk through. And Andre's going to talk through some of that. And then maybe the implement NAT, DHCP, we'll talk through that issue. That'll be another one. And we talked about hardware VTEP in another session. If we have time, we might try to talk through a little bit of the hardware VTEP pieces. So hardware VTEP. Actually, do you want to go ahead and you want to come up and talk? Yeah, so this is Andre Fredette on our team, and he'll talk through the SFC stuff. Sure.
All right, and then is this one off? Okay, as Sam said, my name's Andre Fredette. We've, over the kind of course of this week, we've talked to a lot of people about supporting SFC, and a lot of work has gone on already between SFC and the GBP project, and you've heard a lot about that. And what we've been looking at is basically using, learning from what they've done and pretty much using the interfaces. And so to kind of think about how to do it, we have to work through where's the information coming from. And this is, I think there's still a lot of things that are in flux, but this is close to, I think, the way things would happen. And I don't know if I can use that so you can see my pointer there. So I'm going to go over kind of in general how the data flow, and then come back to what we would need to do within Netverte to support the service function chaining. So from some high level orchestration of the user, the tenant VMs, networks, et cetera, are created via OpenStack, and then the flow comes through Neutron into OVSDB project, just like we're doing today. So these networks will be set up in that manner. However, it is important to use SFC, it's going to be necessary to redirect some of the traffic from some of those tenant VMs onto service chains. And so whoever is doing this creation might need to know some information about what's being created, in particular port IDs and tenant IDs, et cetera. Within the SFC space, VNF, there's a VNF manager that will create additional VMs. We hear about them as normal tenant VMs, but these are VMs that are running service functions, firewall, NAT, et cetera. And they're created by this VNF manager, and then it needs to know information about where they are, because the service SFC is going to be building a service chain, service chains from these functions. So get created by OpenStack, and then VNF manager would need to know. I mean, there are different proposals on how this would work, but in general, you can create the VM and then find out what's the port ID, and then whenever the port ID shows up on a particular vSwitch, you could then locate it. SFC manager is going to need to do some additional work with that, but that's not That's not our job. That's up to SFC. Once we have the user VMs and the service functions created, the VNF manager would need to create service chains. And so inform SFC, these are the service chains you need to build. Here's where your service functions are. So then the orchestration or user would need to say, I want this traffic to use this service chain. And that would come through, and I'm envisioning some type of match, so a certain set of conditions. This is the classification. So define a classification and then identify the chain. So it might say in this match, this particular port, traffic received on such and such a port, physical port, or neutron port would need to go to, that's destined for port 80, HTTP traffic, should go through a particular service chain. So there'd be some type of kind of ACL to map that. Once OVSDB gets this information, it makes a request via MDSAL, an interface that's already been created for the GBP SFC integration to tell SFC, hey, I need to use this service chain. And then there's a response, again, through MDSAL that provides acknowledgement and says, here's where the service chain begins. I kind of skipped, so at the point where a service chain becomes needs to be used, the service function SFC would render the service path for that chain. So a chain is a logical sequence of service functions. The rendered service path is the actual instantiation of that chain. So it goes down, SFC goes down, actually programs flows in the, currently it's a separate set of bridges, OVS bridges that support the network service header to direct the traffic through the certain chains. Not something that within our project that we need to worry about. That's their job. So it's kind of a separation of responsibilities. However, for us, we would need to, once we get this information, put rules in the switches to redirect the traffic and send it on the traffic that would perhaps normally go across one VXLAN tunnel at the bottom. This is just an example from VM1 to VM2, would now need to be redirected through the service chain on also a form of VXLAN, but it's an extension that includes this VXLAN, GPE, can't remember, general something, something extension. It gives you a next protocol type. So it's a way to shim in the network service header, whereas the existing VXLAN just assumes it's a layer 2 packet. And then at the end of the service chain, there needs to be a way to get the traffic back into the VM. There are a couple of different ways of doing that currently. For example, in the current demo, what they do is there's metadata that's included in the network service header. And what the GBP project does is grabs the destination IP for this tunnel, the original tunnel, the VNI for that traffic, and sticks it into the metadata, and at the last hop, the service function forwarder would pull the metadata out and put it back in the packet and send it to the ultimate destination, assuming it didn't get dropped. So what would we need to do to make use of all this infrastructure? And there's probably some other options on how to do that, but that's still work in progress. But so I highlighted here in red what I think are the things that we would need to do to make this work. So at the top here, we would need to implement this classification API or ACL API. And one source for that, SFC actually has one, kind of a simple classifier that's already been implemented by SFC. Certainly we should look at that. But I'm thinking, given that this is Neutron, we're dealing with OpenStack created networks, we might want to do rules like have a match on a tenant UUID, the port UUID, maybe the network, and then all the rest of the IP headers would be fair game as well. we would need to use this existing API to communicate with SFC to say, I want this chain, where is it? And then we would need to implement the ability to add this VXLAN GPE tunnel with an SH header on our BR int, I believe, so that the traffic plus the flows that are necessary to do the classification and grab the traffic, and instead of sending it on the normal path, send it on the path for the service chain. So that's pretty much the high level. Any questions?
So the SFC functions, right? So they all operate in the L2 domain, or would it operate in the L3 domain as well?
The functions?
Now the SFC itself, I mean, you go through a set of rules, right? When you go through each of the service functions, right? So would they all be before the packet leaves that particular L2 domain itself, or would they happen anywhere in the path, in the transit part of the remote location?
So that's a good question. I'm actually not sure of the answer. I know that it's highly flexible, how the service chain can work. It can look at anything in the packet, potentially redirect it to a different chain. I suspect that's also a work in progress. I don't know if there's anybody else in the room that can answer that.
So the network, the service having the path or the path that itself can do anywhere, but it has to come back to the service level, and then it resume its path.
Yeah, the service function. Oh, yeah. I didn't draw. This is a drastically simplified diagram, but yeah, there would be this SF would actually be attached to what's called an service function forwarder, SFF, which is another. It's an OVS switch that can deal with the network service header.
Yeah, and everything's forwarded through a VXLAN protocols. So packets in SH header, and then the real pair. So everything, so at that point, once you're going off the VXLAN, that's the beauty of the NSH. Pass it off to VXLAN and go in. So it's forward towards the SF. The SF understands NSH. So it works on, works on packets, slaps the header back on the packet.
Yeah, I mean, what
Yeah.
do the service function can even before I do the VXLAN kind of right? You would decide whether I should put a VXLAN or not. So
Well, but currently the SFC works with the VXLAN tunnels. There are different ways of doing it. It's been done with VLANs. It could be done GRE tunnels, or just it could be done a lot of different ways. But the current SFC project makes use of VXLAN GPE with the NSH header. I thought you were asking, is it possible that, so we have, this is really showing VM1 talking to VM2 over a layer 2 network. I thought what you were asking was, would it be possible for, say, one of these service functions to route it someplace else in a different layer 3 network? I don't know. Typically, these are the flows that I've seen discussed are all within the layer 2 network, but I don't know.
But nothing is stopping it from forwarding it because of the network service header. We just have to
Yeah.
do that for it to be.
Right.
no question. So this ACL APIs, are we creating a new model, or are we going to use open source?
No, I think we would. I don't know. I was thinking we would create a new Yang model to describe this, unless there's one that already exists within SFC that we can reuse. But
This is for matching the flows.
yeah, so it'll be, maybe we would.
Already has,
Yeah.
plugin already has.
So I think we could maybe make use of a lot of that. I don't know if it would be exactly the same one. Sam, what do you think? Any?
You could, I think the problem is, those open flow models, let's go to open flow, and they're kind of very specific. In this case, if I'm hearing the same in the OpenStack, we haven't had anything word on tenants.
Yeah, so it could be a richer API.
That's the problem. Of course, parts are going to be L2, L4, you put the open flow function stuff. But there's extra things.
Yeah. We've talked about you potentially using the network intent, the NIC API as a higher level abstraction layer to describe these classifiers. That's a possibility. Probably not the first step.
Yeah, potentially, we are basically these are the flows we are feeding into your classifier before your service function saying instance starts. That's the bulk of the.
That's the main purpose. The traffic's coming off of you gotta keep. SFC is really good. Once you're on that chain, it will all work. You gotta get into it, you gotta get out of it, back. It's a little classifier there. And that's, the way it's depicted there, it comes in off that beat, and it's just redirected off the SFC.
Yeah.
Right now, they already have in the IP tables. Now we are saying that we want to start flows on open research. That's the purpose.
Yeah, there's two demos, yeah. One of them is actually demo based, one actually there is some flows. It's very simple, DB policy, DB.
Oh yeah, that is DBP.
Yeah. Yeah, the other one is like tables.
ECL API application is basically it's some sort of classifier that would put it into the chain. But coming out of the chain, maybe we need to have some sort of logical node or something because you need to get into.
Right. So this is the it's you could do a lot of different things. You could, when it comes out of the chain, you could basically reclassify it and figure out again what to do with it. In the simple flow, where it's if you already at the ingress, you've decided where it needs to go, you can run it through the service chain, and then as long as it passes through, it can still go to the same location. And the current options kind of on the table are the way that GBP did it in the demo, which is you figure out where it's going to go to start with, and then put that information somehow put that information into the metadata, so that this last service function forwarder here, which I don't have shown, would know, hey, I'm the last one on the chain. Let me strip off the NSH header and VXLAN GPE and put on whatever, in this case, a VXLAN and then VNID to the original destination. I guess it could be rerouted. That might not be the best way to do it. And I was talking to Brady Johnson yesterday about the other ways to do it. Maybe there could be some signaling here where we signal basically the what to do with it when you're done, and then maybe put some type of ID rather than explicitly putting the header information in the metadata. Put some type of cookie in there that would allow that last service function forwarder to send it to the right place. I mean, but you might also have to basically hand it back to a forwarding element to figure out where to send it again. I mean, that's, yeah.
This is the OpenStack world. The SFF's really good around this integration. We're already managing it pretty well with the overlay there. Things come in on the PRN, pipe along to the SOC. Eventually, that last SFF that pops out on PRN. So as long as we've got enough information to what we're doing now for metadata, passing the tunnel ID, basically tenant ID, the destination ID. That information will be right back in the pipeline. Just like regular.
Similar to MPLS last time.
Yeah, exactly. So those flows on the inside, the ingress, it's almost like you've got a pier on the egress side, very, very similar. As long as you pass that information, you stop it back on, right back in the pipeline.
So what about the complex cases where one of these elements rewrites the service string?
Yeah, I know, that's, yeah.
When you say rewrite,
I think there's a lot of stuff. This is an area that it has not been figured out yet, and there's a lot of discussions going on. And frankly, all of this stuff we're talking about is going to be the same for whoever integrates with SFC. So there's GBP now. We're talking about doing it. L3 VPN is talking about doing this integration, and I think these are kind of SFC, discussions and things that we're going to have to figure out, and then they'll apply regardless of who's the Netverte provider, I think.
There is a group-based policy effort in OpenStack. So how does it tie in with respect to that? Is it a parallel effort?
Yeah, so the group, I mean, it's,
If you want to look at so SFC, it does all the pieces. It does the service tuning. What GDP does today, this classifier. It was so SFC had it has an ACL, but it has no idea about VMs, the tenant, where everything sources from. It's got to get into that chain. So what GDP has that policy. It says, hey, let's create a new action called chain. Let's get an ACL. So now they can apply that flow. That was a way for them to put that initial ACL flow there, so they can get tracked into the chain. Okay, so and on the network side, that's exactly what we'll do. It's a very similar type of operation.
so it'd be a different API. I mean, would OVSDB Netverte be a provider for this OpenStack GBP, if that ever happens? I don't know. I mean, maybe not. But then there's also the possibility of having using the network intent as your top level abstraction, and then having Netverte be a renderer for network intent has been discussed. I don't know. Probably not this release. So I had just on the slides, there's just a list kind of these things in red just spelled out a little. We have to work more on it, want some more details. So it's kind of there for the record. I don't think there's anything new here. So any more on the SFC? Probably, I'm sure we'll be talking about this on the calls and on the list and such. Sure.
So what about that middle line, the ACL API?
Yes.
Where's that?
Yeah. So that's a new interface for Netverte. So.
We talked about using the range interface.
No, it doesn't currently. So there's also a discussion of there's also a nascent, SFC effort within the OpenStack, and so it's possible that could, if that makes, develops, it could come through OpenStack. But currently, the way that the architecture is defined is coming in using either from VNF Manager, whatever this blob is, which there's lots of some options there, or just from some top-level service orchestrator that says, hey, I know, he's kind of saying, okay, I created these VMs, I'm going to create some service chains, I'm a user, I'm creating my virtual network, and I want it to run, for web traffic, I want it to run through these service functions, and so I'm provisioning the network to create it and then run it through the service functions from some top-level API. So currently, it's just coming in through a REST API. Yeah.
Well, that's
Yeah.
current.
Yeah, it's a REST API currently.
So the ultimate architecture being OpenFB, it's that some sort of service orchestration, and there's that DNF manager. Current demo that's out there, what's really happening is the DNF manager and service orchestrator are not there. They're OpenStack.
Yeah, this
Icon scripts, which are sending REST SFC calls and GDP calls. So that's but what the assumption is once that migrate to the OpenFB architecture, that would be driven now from that DNF manager and that service orchestrator.
and all tied in and possibly through OpenStack or possibly not.
That's the piece which is smarter related thing.
Something needs to tie it together though up there. All right. So just list the tasks. So the next I want to talk about, yes.
Was
Yeah, they're actually they're actual VMs that are known by OpenStack.
So there will be an OpenStack or I can show these ports and OVSDB. They're looking at operational extensions for their, for the network way. Some things is not the way
Yeah, SFC, I think there is a UI for SFC right now, kind of put stuff together on the deluxe page. But of course, all this stuff, it's all back, it's all used out back. All every single element, every single flow, every single port, every single query.
So from a deluxe, would I be able to figure out that this particular flow is following this SFC chain?
I don't know if it's that. There is SFC deluxe, I'm just not sure.
I mean, but that's actually what might be within, like say in our case, Netverte, to identify that the flows that are the classifiers. I mean, we need to be able to show the classification, I guess, and the service chain ID. And then you might need to trace it into
What I'm saying
SFC.
is that if I already knew what the service chain is, then I can follow it, but I click on a flow and I want to know what service chain is going through. That's what the
Yeah, that's
because we don't want to
yeah.
remember.
Well, none of this is there yet. So, yeah, yeah.
So I think SFC deluxe and what all they do is they fetch the stuff from a switch and they just show it. So you know what output flow you install, so you can show it in that way. But otherwise, without context, open flow switches don't know. They don't really know. It's just a flow for that. Right? So whoever does that, they can orchestrate that and say, okay, this is my service field chain. These are my flows which are responded.
Yeah, but I can see from a just kind of usability standpoint, it'd be great to be able to visualize your network and see what's happening, right? Because that might not be all the traffic. There's just certain flows, and then you might even have certain flows originating from that VM that might go through a different service chain. You have certain flows from other VMs that go through that same service chain, so it get complicated. So yeah, that's definitely some usability considerations here. Ready for NAT yet? Okay, I want to talk about NAT. So what, I think Flavio did the floating IPs, right? So what's implemented right now by Flavio is the floating IP support. So I want to talk about the different kinds of NAT. And we've been calling it, if you've been on you see some of the Trello board, and we've been calling it SNAT and DNAT. And we've been calling what we're doing now DNAT. And I don't think the terminology is quite right, so I just wanted to put up here the different types of NAT. So there's static NAT, which is effectively what we do now with the floating IP. So you have a static for every internal IP address, one-to-one mapping to an external IP address, that's the floating IP. And when you go through that NAT function, it swaps the source IP address on the way out, swaps the source IP address internal for an external one, and on the way back, swaps it back and comes in. So we got that working. But then there's also within OpenStack and within the current L3 agent, and probably everybody's home router, a dynamic NAT function that's most likely, and there's different kinds of dynamic NAT. One is with floating IPs, we statically configure a one-to-one mapping. With standard dynamic NAT, there's a pool of those, and it'll dynamically allocate them, as needed. And then if they time out, it'll free them up. But then what probably most people use is goes by many names. And I've been just doing some looking around. But so single address NAT. So you can share a single external IP address by multiple internal addresses. It's also called overloading, masquerading, port-based NAT, network address port translation, NAPT, and port address translation, PAT. But so the last one is probably one of the more common ones. But basically what happens is that the external router has only one or maybe a small set of external IP addresses. And then the router dynamically maps the internal clients to the external addresses using the TCP and UDP ports, so they have layer 4 ports. So I just have an example there of a table that perhaps you have a packet coming from 10.0.0.1, port 5678. it could, and then we have one external IP address, 203.22.11.20, and that would get mapped to the IP address, but then also map the port on the way out. And then on the way back, you look at both the port, the destination port, and the destination IP, and if it matches that entry, it would get mapped the other way. And you can use that same IP address, external, with different, even the same IP address with a different port, or a different IP address with whatever ports. And then we just have to manage that port table. The key on the way back is the IP address and the port. So these are with the floating. So there are a few issues this brings up for us with the floating IPs. It's a one-to-one mapping, so we know static and we know ahead of time, so we can pre-program the flows to do that. So that's great. The second thing is every internal address has a different external address. And so on the reverse path, and let me maybe go to the picture. On the reverse path, if this is your external router, the packet's coming in and it needs to go to, if I've got 10.0.0.1 belonging to say, so okay, well, I'll just use these IP addresses that are on here already. So didn't have time to build a fancy slide, so I'm just going to try to talk through it. But on the way out, let's say okay, so you've got, and this is the public, this is the floating IP, great. On the way out, .5.3 is going to get mapped to this address. On the way back, as it's coming from this router, the address is that it needs to go to is this 192.168.56.10 address. So what the router is going to do is they're going to ARP for that address, and we know where it is, and so we can reply with the MAC address of this. I'm not sure which MAC address is it. Is it of the BRINT? The MAC of the floating IP. So there's a MAC here, but the key thing is it's only on one bridge here. And then if, likewise, when this goes out, it goes to .56.11, which on the way out, fine. On the way back, this router to get to it's going to ARP for .56.11, and it's going to get a MAC that lives over here. And the packet gets forwarded, and then when it gets into BRINT, we swap everything back and send it into the VM. Now, the problem that we have on the reverse mapping, if we're doing this, the port address translation, it's actually reasonable on the way out. We're translating, say, to the same IP address, but with different ports, so it heads out fine. But on the way back, it's going to ARP for that IP address, that external IP address, and it's the same IP address for all of the compute nodes, or many of them potentially. And so we don't know where to send the packet. The router doesn't know anything about the NAT because we're doing it, and so we have this problem. So that's the first problem, is how to get the packets back. The second problem is that we just can't do it all ahead of time. There's too many possible translations. It all depends on the data flows and what TCP ports they use. And so typically it's done dynamically when a new flow, if it doesn't already have a mapping, it gets dynamically created on the fly. You allocate a port from an external port from a pool and set it and program your table. So, one way to do that potentially is to use the controller and packet ins. And if you have a packet going out to the external router and you don't already have a flow, you'd need to punt it to the controller, which would look at it, allocate a new port, a new mapping, program the flow, and then send the packet on its way. So that's a little more. We currently don't have that kind of dynamic, reactive flow provisioning in what we have. So those are basically the two problems that we need to solve. So that, I'll I'll talk about the second problem first because it's, it's a little more straightforward. The first one is to just use the controller. This is actually a really good job for if there's for a local agent. If we had a local agent out here on the compute node, that it could all be done locally. You could break it up in they could each get a pool of ports and could handle it all locally. But we don't have that. So this is I think I may have said should have said when I started is that I don't have all the answers for this, just some of what the problems are and a few solutions, but there might be some really much more intelligent solutions. So yes.
Sorry, one dumb question. I would expect the NAT functionality to happen in one probably centralized or probably the outer one.
Yeah, so that is a possible solution. So that's the way it works right now. So there's a centralized, this is actually the L3 node, and you communicate with it, and it does it there. Yeah. So what I'm exploring here is so one possibility. So what we're trying to do is look at what we did in Lithium was to create distributed virtual routing. So we've got this virtual router, and all of the forwarding happens in a distributed way. Instead of having to go through the centralized layer 3 agent, it goes directly from node to node. And we're looking at, well, can we do the same thing with NAT? And we have these other challenges in doing that. But so yes, one possibility is just to have this guy do it. Have a router. But then the problem is that has to be a member of all of the tenant networks that it's supporting. So do we have, could we use a layer 2 gateway when we get it, plus an external router that can have a lot of virtual, basically implement a bunch of virtual routers, each connected to a different tenant network and do the NAT functionality for us? Good option. Could we kind of make use of the layer 3 agent, or some trimmed down layer 3 agent that just does NAT? Could we, but we don't want a centralized, bottleneck. So could we use, say, multiple of them in a VRRP kind of model with, active, where they're all active. We can load balance across different flows across them. So I didn't have time to kind of write down all these options, but these are some of the things we've talked about.
I thought, putting it in a centralized place, right, you could also have probably some more sophisticated services also, like you can do firewalling as well.
Yeah.
In a centralized place.
Yeah.
So I think NAT and firewall pretty much work pretty close to each other, right?
Yeah. Yeah, or is this a service function that's on a service chain? I don't know. Yeah, but that's my favorite solution is to punt it on this one because it's pretty tough.
Away from this single point of failure, that's where we get the cable distributed. We do not want all the traffic routing to a single node. So the push schedule to distribute as much as not a single point of failure. So it can be done, but really this is a single point of failure and it's schedule issue.
So let me just get the one other thing that I want to say about this was on the return path. One way to solve that is instead of having one address for everything, you could actually allocate one address per node, per BRX. Perhaps from the floating address pool, we can allocate one. And everything's not being shared by one external IP address, but everything on a given, connected to a given BR int would share that one IP address. And that way, we could handle the issue with where does it go when it comes back. So yeah. So my thought is if we could just come up with a way to do it externally, so with a L3 agent type solution, with multiple agents in a centralized location. If that's simple to do, that'd be a really good first step, and at least we have the functionality. And then, as a second priority, work on the distributed solution, if it makes sense. But I'm concerned about that, the load on the controller with the flow setup, the reactive flow setup. But it could be done. We could see how it works, see how it scales. So
Also, there is OVS considerations there, right? Because one of the things is that TCP packet will be fragmented and may not have full information if you're looking at the 10th packet in the disk or something like that. So, I mean, with that impact, it's a little bit more tricky. Can the OVS actually do it based on the functionality that exists, or do you need additional functionality?
can the V?
Because it's not essentially it's a IP to IP map.
Yeah.
You need actually try to look at the port location as well as the IP information. Let's say this week I got fragmented so all right,
Yeah. It still has a TCP header on it though, and it still has the. What's that?
TCP header would be there probably in the first fragment below. IP fragment. Other IP fragment. If it is IP fragment, TCP header is only a first fragment. So then we're looking at one segment and then the rest of the fragments are not.
Yeah, so that's a good something to look into.
If OVS is capable of reassembly, it's easy. I'm not sure.
Yeah. Okay.
So I think that actually try where do you want to traffic to go in because if you have a nut on where exactly is the nut?
So we're talking about two options. One is basically the NAT is over here in the router. That's the centralized option. That's easy, pretty much. But the tougher, we're talking about a distributed option where the NAT functionality is actually being performed on these BRINTs before the packet gets sent to the router. That's currently where the floating IP NAT, the static NAT, is being performed currently in this BRINT based on OpenFlow rules.
So can you overcome them by defining some interfaces?
Can you?
Defining some interfaces on the main interface, external interface, another interface, using VLANs, right?
Right. If we want to use this as an external.
No, not you can on the OVS. You can on the machine that the OVS run on. You can define some interfaces for the Ethernet one, for example. And then you can assign those some interfaces to the VRINT, and then you kind of getting slices from the Ethernet one, right? And if you assign a VLAN to those sub interfaces, you can assign the same VLAN to the VMs. You get it nothing, right?
Yeah, but in this case, these VMs are both on the same layer 2 broadcast domain. So they'd have to be on the same VLAN. What's that?
Are they on different machines?
They're on different machines.
So if you assign the same for each VLAN, for each VM, each port on the OVS, you assign a VLAN. You can and then you assign the same VLAN sub interface on each Ethernet one on the VRINs. They're going to communicate with each other, right?
I'm not sure what problem you're trying to solve.
So it sounds like you're talking about just the VLAN networking supported by OpenStack, and that's what they do, right? To put all of the, so what we call the router network, you're putting onto a provider network, which is this VLAN. That's supported too. In this model, it's the VXLAN using tunnels to
I'm not, are you thinking that it will solve one of these problems with the distributed NAT? Yes. Are you suggesting that as a solution to one of the problems for distributed NAT? Yeah, they're using this, that's the way that the shared IP NAT works, that once it goes outside of the NAT function, they have the same source IP address. And that's the way your router at your house probably works, and at many small businesses anyways.
But what Sharon is referring to is also, there is a one-to-one NAT and there is end-to-one NAT. What you're referring to is the problem of an end-to-one NAT.
Right.
Needs connection tracking, needs to be handled by a single interface, otherwise it won't work. And most probably will have to go to the router node. And a lot of time OpenStack's been used to use more one-to-one NAT when you allocate a single IP addresses for every internal IP addresses that you want to expose the machine, and you want to also from external places to go into the site the OpenStack. And a lot
Right.
of places on the one-to-one NAT you can do that in every machine. And it would be good to go into the machine like the DVR. But why not do that in OpenFlow? You can set up the OpenFlow rules to stack on the source IP addresses, and then just to handle ICMPs or things that are missing on the decoder loop. Why not do that inside the OpenDaylight?
Yeah. Yeah, we currently support within OpenDaylight, within the BRINT, that one-to-one static NAT mapping. So that's already done and it's fully distributed. And the problem we're talking about is, could we do the same thing for this end-to-one mapping, NAT mapping, and can we still do it in a distributed? Can we still do a distributed implementation of the many-to-one NAT mapping? No, I can't remember the old days very well. I'm not. I don't quite follow what you're saying. We're trying to use a single or small set of IP addresses, external IP addresses, in this case one for many internal addresses. Right. Yeah. Yeah, that all works, I think. Actually, so are we hitting the end of the session? Do you want to wrap up, Sam? We can continue discussions hallway or offline. Anything else? All right. Well, thanks for coming.